Option Greek delta. The framework we're going to use is as follows. First, let's have a look at a long call position. And the starting point is to see what the intrinsic value of a call option is. Now, a call option says you have the right to buy the underlying asset for a particular strike price. So if the price of the underlying asset is greater than strike, then the option is considered to be in the money, because then it would make sense to pay X in order to buy an asset that's worth ST. On the other hand, if the price of the underlying asset is less than strike, then it wouldn't make sense to pay the strike price in order to buy that underlying asset, and therefore the option is set to be out of the money. And of course, the final scenario is if the spot price is equal to the strike price, then the option is considered to be at the money. But again, I want to emphasize the key point. The intrinsic value, which is our starting point here, would be represented by the lines that I'm squiggling right now. But what that tells us is that it tells us what the payoff would be if we simply exercise now. But suppose that the option still has a few months left. You could see that the downside is limited. The worst thing that can happen is the payoff will be equal to 0. On the other hand, you could see that the upside is unlimited. So the fact that we still have some time left for this option before it expires implies that it has time value. And what time value indicates or represents is the potential for an even higher payoff before the expiry date. So then what we're going to do is we're going to take the intrinsic value line, which is what our payoff would be if we exercise now, and then we add this time value, and the combination of that intrinsic value and time value is what the option will be trading at today. So therefore the red line, this red line here, represents the actual price of this call option. We're going to do a similar exercise for a put. And as we know, a put is a right to sell for a predetermined strike price. So if the put price is over here, or I should say the price of the underlying asset is right there, then I'll gladly be willing to sell it for the strike price, which is higher. Then the put would be considered to be in the money, because if you exercise, you would make money. On the other hand, if the value of the underlying asset is here, then it wouldn't make sense for me to deliver this asset and only receive strike for it. So therefore the put would be considered as out of the money. And of course, in the chance that the spot price is equal to strike, then the put would be considered as at the money. And we're going to do the same procedure for the long put as we did for the long call. And that is, we're going to start off by looking at the intrinsic value first. So the intrinsic value is represented by this line, which I'm squiggling. And the intrinsic value, again, represents what the payoff would be if you were to exercise right now. So if you exercise right now, you'll get the difference between strike price and the spot price if you're in this area, or it'd be 0 if you're in that area. But ladies and gentlemen, this option may still have some time before expiry, and that means it's got the potential for an even higher payoff. See how your downside has a floor, whereas your upside is more? So if you have time remaining, this is referred to as asymmetric payoff. The upside is greater than the downside. So therefore the option is going to have time value as well. So the combination of the intrinsic value, i.e. what you can get if you exercise now, plus the possibility that you can get even more before expiry, gives us what the total value of the put option would be. And again, that's represented by the red line. Now, where does delta come in all this? Delta is the sensitivity of option price to change in the spot price. So if you're looking at the delta for a call option, there it is. It's the sensitivity of the call price due to changes in the spot price. But ladies and gentlemen, if you come back to this visual framework, change in call over change in spot, well, that's your rise and that's your run. Where's this going? Delta is represented by the slope of the red line. That's it. So there it is. Delta is the slope of the call price, which is represented by that red line, which takes the combination of intrinsic value and time value. Ladies and gentlemen, why is this so exciting? Why is this super exciting, because even if you don't know anything about delta, I know that if you go back and look at your grade 5 math notes, you will have something written down about slope. So if you can explain what's happening to the slope, you are in effect explaining what's happening to the delta for that option. So let's have a look. Again, we're zeroing in on the call first. So if the spot price increases, let's go see what happens to the slope. Now, we've already constructed the red line, so we explained in detail why it's shaped the way it is. So we don't have to reinvent the wheel here. We just want to know what's happening to the slope. So here it is. As the spot price increases, I could see that the slope is getting steeper and steeper. And that's exactly the point we make here. The slope steepens, which means that delta is increasing. In other words, it's approaching 1, like 1-to-1 sensitivity, and you can see it right here. We just got to go back. This is a 45-degree angle. This line here is 45-degree angle. So as the red line sort of parallels that intrinsic value line for high levels of spot price, then that means there's a 1-to-1 relationship between what's happening to the call and what's happening to the spot price. And you can see it here as well, ladies and gentlemen. Let me show you something. Look at this. So we're going to pick a big change in spot price on both ends. And I want you to see the impact it has on call price. So at this level, you can see that there's very little change in call price because delta is very low at that point. But for that same change in interest rates here, look at the difference in call price. So the point I'm trying to make here is that the call price is becoming more sensitive. In other words, its delta is higher as the spot price increases. And we can go the other way as well. As the spot price decreases, the slope flattens. Let's go see if that makes sense, and it does because we just talked about it. So if the spot price is going this way, let's see what's happening to the slope. So starting from here, because the price is dropping, so you can see that the slope is getting flatter and flatter and flatter, and therefore delta is decreasing. And what does that mean again? The sensitivity of the change in the call price is getting less and less sensitive. Now finally, when the call is at the money, delta would be equal to 0.5, and that's talking about right here. So if you were to find the slope right there, it'd be 0.5. So what are our extremes? At very high price levels, as we talked about before, the slope here is at a 45-degree angle, which means there's a 1-to-1 relationship between the call price and the spot price. So the delta here would be 1. Delta here is 0.5, and over here you could see it's sort of flat. So at very, very, very low spot prices, the call price will not even react. In other words, its delta will be equal to 0. So therefore, the range for delta of a call is the lowest value you can take on is 0. And now you know where that would happen. That would happen if the spot price was very, very low. On the other hand, at the upper end for delta, it would be +1. And you also know when this would happen, as I showed you visually, but you can also look at it from here, based on our notes. As the spot price increases, delta increases. So the most it can increase to is +1. So that happens when the spot price is really high and the call is deep in the money. So now let's pick a number that's in between this. So rather than just looking at the extremes, i.e. 0.5 and 1, how about if we pick something 0.7? So what we're going to do is we're going to take our delta framework, and you can see that the delta framework is a ratio, right? You have a numerator and a denominator. And what I always like to do with ratios is I like to flatten it out. That's exactly what I mean by flattening it out. So instead of having a top line and a bottom line, I just want to have a flat line right there. And plug in 0.7 for delta, and now you can see precisely how this call option is going to react in response to changes in the spot price. So if the spot price goes up $1, the call option value will increase by 70 cents. On the other hand, if the spot price drops $1, then the call option value will drop by 70 cents. And again, that's why we say delta represents sensitivity of the call option to changes in the spot price. So now we're going to do the exact same analysis for the put option. Again, delta is how sensitive is the value of the put option in response to the change in the spot price. And again, this is the slope of the put price, which is represented by the red line. And we'll go to the graph in a second, but you'll note that the slope of the put line, and therefore its delta, is negative, because as we know, as the spot price increases, the put goes deeper in the money. So let's go have a look at our graph for a second. And here it is. You can see as spot price increases, the value of the put decreases. So that explains the negative delta for a put. And so now that we know that the delta is negative, let's just concentrate on its magnitude. So we're not going to keep saying it's negative, negative. We know it's negative. Here's what strikes out from this visual framework. At very low spot prices, you could see that the slope is at a 45-degree angle. Yes, I know it's facing down. We talked about that. It's negative slope, negative delta. But here it's like -1. And here, check out the slope. It's almost 0. So here, it's 0. And similar to the call option, when the spot price is equal to the strike, then you're at the money, and at that point the delta is 0.5. So that's where we're getting the delta values for put. It's simply the slope of the put price. And this just elaborates on what we discussed. As the spot price increases, the slope flattens out, therefore the absolute value of delta is dropping. It's approaching 0. So that means the value of the put is becoming less sensitive. On the other hand, as the spot price decreases, the slope will steepen. That means the absolute value of delta is increasing. And at the most, it's approaching -1. And finally, when the put's at the money, we said that its value would be 0.5. But because it's downward sloping, it'd be -0.5. So therefore, the range for put delta is -1. When would that happen? And again, this is why those visual frameworks are so powerful. You don't have to memorize anything. You just have to look at your visual framework. So when does delta really increase? When the spot price is dropping. So at very, very low spot prices, you get a delta close to -1. On the other hand, when would it be approaching to 0? And again, we've covered that as well. When the spot price is at a very high level, that's when delta approaches 0. Let's do an example. In other words, let's pick a number that falls within that range. What if it's -0.3? Same process, ladies and gentlemen. Same process. We take delta, which is a ratio, we flatten it out, and then we plug in what the delta is. It's -0.3, and there it is. So if the spot price increases by $1, multiply that by -0.3, that means the value of the put will decrease by 30 cents. And again, a put is a bearish play. So you only make money if the spot price drops. So if the spot price drops, -1 times -0.3 is +0.3. You could see that the put actually makes money when the price of the underlying asset drops. Now let's also have a look at the delta for the underlying asset. Now remember what delta is. It's the sensitivity of the security to changes in the spot price. But if the security is the actual asset you're trading, of course there's going to be one-to-one relationship. And similarly for forwards, the change in the forward price, because if you recall, forward price is a direct function of the spot price. So you could see that the delta between the forward and the spot price is approximately equal to 1. So for practical purposes, ladies and gentlemen, whether you're looking at the underlying asset or the forward, unless you're told otherwise, the delta is 1, even for forward contracts. Now tip, the above deltas were for long positions. Therefore, for short positions, we simply reverse the algebraic sign. So rather than doing a brand new module for short option deltas, which would be ridiculous, we would just take whatever deltas we've calculated for the long positions and just reverse the algebraic sign. So for example, if the call has a delta of positive 0.7 for the long, then the person who's short that call option would have a delta of negative 0.7. Therefore, if the spot price increases by $1, the long position would make 70 cents, but the short position would lose 70 cents. And that makes sense, right? Because we know with options it's a zero-sum game.